Well, thank you very much, Ken, and thank you everyone here at the Institute and the fine tour I've had today. It's just really been enjoyable. And I do believe this is my first return to Pensacola since I was given a check ride by a gentleman here in an audience and turned loose after only 8 hours in one of those H-13s. When they told me we were going to solo after 8 hours, I said, "You're crazy." But they turned us loose, and that's great. Ladies and gentlemen, what I want to do tonight is take you on a very quick trip to the moon, talk a little bit about both history and some of the things that might happen in the future in the context of that trip. Of course, we began it, as this gentleman down here has reminded me, with a launch of a Saturn V, the largest rocket used by human beings to go into space so far, and indeed will probably stay that way. The Saturn V weighed 6.8 million pounds, fully fueled. Developed 7.5 million pounds of thrust with the initial first stage, the 5 big engines that were in that stage. And as I said, really was a remarkable accomplishment. Those of you who may have glanced at my book, I still say that over the long haul, it's probably the concept of a rocket system that would sustain us best in long-term access to space. But be that as it may, there are other circumstances that have required NASA to move towards a shuttle-derived system, primarily economics, relatively short-term economics, because tooling is available for that new rocket, where it's not available to the Saturn V any longer. Now, the trip to the moon required, as many of you are aware, some 450,000 Americans to work together. Only 50,000 of those people were actual government employees. The rest were part of the contractor team that supported that mission. Okay. And most of those people were young. Gene Kranz, in his book, Failure is Not an Option, which I strongly recommend to you, notes that during the Apollo 13 crisis, he did a rough calculation of the average age of the young men and women who were then in the Flight Control Division, basically rescuing Jim Lovell and his crew. And that average age was 26. And we have to remember that when we talk about going back into space, we talk about doing any large-scale activities, you have to have that really a core of young men and women that provide the imagination, the motivation, the stamina that is necessary to carry off these kinds of projects successfully. It is a major issue for the country right now in how we stimulate our own citizens to take on those kinds of, the kind of education that allows them to participate in these kinds of projects in the future. NASA is approaching a time where they will have something like 25% of their workforce retire. And that's not only true of NASA, it's true of a large component of the aerospace industry. And that, who's going to fill in behind that 25% is a major issue that the NASA Advisory Council is dealing with. Ken Ford is sitting on that council with us now. And it is something that all of us have to worry about. Okay, we'll move quickly now. We've talked about Saturn V. We also did a great deal of geological training. This is yours truly there on the left, my robot assistant on the right, Gene Cernan. Actually, Gene, like all of the commanders of the missions from Apollo 13 on, became excellent field assistants, in fact, to some degree, geologists, through a training program that we put together. This part of this training was for the last 3 missions at least. We had about a week a month, actually out in the field, working actual projects unknown to us, but following through in a simulation-based set of procedures, doing as much as we could exactly what we would do on the moon. Of course, we didn't wear our pressure suits, spacesuits, but we used all the equipment we had available. You can see the backpacks and everything that were simulated, but nevertheless enabled us to not only learn the geological aspects of exploration, but also to get the procedures down so they were pretty much automatic, rote, and we wouldn't waste a lot of time on them. Now, the reason I show this picture is not to show how I've aged, but to give some of you, and particularly these young people in the audience, always are wondering what all of those colored valves and entry ports are on this spacesuit. This is the Apollo exploration spacesuit. The blue ones represent inputs into the suit, and the red ones represent outputs. Our oxygen, our communications, our water. We had, you know how we stayed cool on the moon? Besides our personalities, of course. We had water-cooled underwear. And in fact, today I just saw one of those water-cooled underwear that they're using up here in some of their experiments here at the Institute. It really is a wonderful way to stay cool. In fact, more seriously, it is what we would call an enabling technology. We could not have spent 8 hours straight in this suit working without some kind of technology like that, other than air cooling or gas cooling. We had to have that water-cooled underwear. Now, the way I'll talk a little bit more about how we cool that probably in a few minutes, but this spacesuit was really an extremely important part of the Apollo program. It's another spacecraft, really. It had everything you needed to work outside the lunar module for about 8 hours. Actually, we were pressurized in it probably for more like 9.5 to 10 hours. And it could be recharged every night or every rest period. Of course, the moon night and day is a little different than down here, but every rest period we would plug in the water and recharge the water, plug in the oxygen and recharge that and put a new battery in, and we were ready to go the next day. It worked out extremely well. To give you a little perspective on the size of the Saturn V, though, I want to show you this picture. This is the vehicle assembly building at the Kennedy Space Center, still used for the space shuttles. Some of you have been down there to see that. But you see just how big that rocket is in comparison. And to give you another sense of scale, those of you who can see down the lower right-hand corner is a fire engine. And it's a big fire engine. That red object down there is a fire engine. So these were big times, big things. And to work in deep space, it takes big things. Because getting off the Earth against what we call one gravity, or Earth's gravity, takes a lot of energy, and to harness that energy takes big rockets like this. This is just give you a perspective of what it was like when our Saturn V ignited. At this point, there was no significant acceleration, you feel, but a very, very heavy vibration. The 5 F1 engines in the first stage were working against each other to some degree. The acoustic shock waves were working against each other, and the stack, as we called it, was vibrating at this low frequency. And that's when I realized that all the simulations that we did in preparation for launch didn't mean an awful lot. I guess it was good training, because the instrument panel in front of us going like this, I couldn't read a thing on it. That's just give you another different view. A few people in the audience, I guess, saw the Apollo 17 launch. I hear it was spectacular. Now, I show you this picture. This is one of the first pictures I took when we were in orbit. We were only in orbit for about 3 hours. We had at 18 miles an hour. Your orbit around the Earth is about 90 minutes. And I didn't have a chance to take a lot of pictures because we were getting ready to reignite the third stage S-4B rocket and head on towards the moon. However, I want you to look at this. This is not an set of ice flows out there in the ocean. It's actually clouds, but over there you get, later on I'll refer to this, you see that blue band at the horizon. That's our atmosphere, folks. Doesn't look like very much there, but it's enough and has been enough throughout geologic time to not only allow life to persist on this planet, but actually to get to the point where we are today. Now, we did ignite the S4B, accelerated from 18,000 miles an hour to 25,000 miles an hour, and we were on our way to the moon. And there you're looking back direct on that third stage, S4B. The Lunar Module Challenger is still tucked away in the end of the S4B. Ron Evans, the third man on our crew, has now taken control of the spacecraft and is moving in to dock with the lunar module so we can extract it and take it to the moon. We could turn out these lights, and I think they'd have a little better view of some of these pictures if that can be done. They've seen me; they don't need to know what I look like any longer. But those, Is it all right? I'm getting a little reflection here. All right, those are pieces of ice. Now, when we sat on the launch pad for an extra 2 hours and 40 minutes because of a computer question that had to be answered and fixed that had stopped our launch at 30 seconds before we were supposed to launch. But we lay there. I went to sleep for a while. You never know when you're going to need some Z's. And but once we were off in orbit, a little bit, most of that ice had come off during the launch. You've seen pictures of launches, and the Apollo 13 movie is very good. They simulated how those big sheets of ice come off the rocket. I thought it was real, and then until Ron Howard told me it wasn't. But a little bit of ice had stayed on this third stage S4B and came off, and you could see that out there. We had a lot of fun talking about it and watching those pieces of ice interact with each other. But they're gradually dispersing. Now, this is probably what former Senator John Glenn saw over Australia and reported as fireflies. Now, John is the former Democratic senator from the state of Ohio. And that could explain that observation. I'm not sure. At about 34,000 miles away, I had the opportunity to take this picture of the Earth. It is still the most requested photograph from the NASA archives. Probably will stay that way for quite a while. It is, of course, shows the entire continent of Africa. And if you look carefully, you can see a cyclone going ashore on the subcontinent of India there, up in the upper right. Antarctica is almost totally exposed. This is a southern hemisphere view because our landing site was in the northern hemisphere of the moon. That's just the way the orbital mechanics worked out, so that we had one of the best views of and we're going to land quite a ways over on what we call the near the eastern edge of the moon, so we had a full Earth, nearly full Earth for a while. Not quite, Mediterranean at the top, South Pole at the bottom. Now, 3.5 days later, we were going into orbit and in orbit around the moon. And this is a picture I want you to remember. You saw that blue band of atmosphere around the Earth? Nothing around the moon. There, you are deep space vacuum on the surface of the moon. The moon it only has 1/6 of the Earth's gravity, and that's just not enough to hold any sensible atmosphere at the moon. For those of you who are into knowing what vacuums are, 10 to the minus 12 torr is what you have at the surface of the moon. And that has a big effect on the weathering of the moon, and indeed there is weathering. It's long-term, slow weathering as a result of micrometeorite impact in that vacuum, and makes a very unique environment which we really can't duplicate down here. We can simulate some of the nature of the lunar surface materials here on Earth, the size fractions and things like that, but we can't really get a good simulant. So this picture actually is of the far side of the moon, and it's a lunar sunset. We were in what the astronomers call a retrograde orbit. That is, we went into the orbit around the moon in a direction opposite to the very slow rotation, once-a-month rotation of the moon itself. And that meant that we were going to land, as we intended to, with the sun at our backs. We wanted to have shadow definition out in front of us of the craters and rocks of any particular landing site. So that was the normal procedure. That's the Challenger, all fully deployed now. A young person some years ago asked me why we put pizza on the landing gear. I had no answer for that. Oops, there we go again. Okay, we'll try that. The Valley of Taurus Littrow, where we were headed on the moon, is a deep mountain valley. You see it here as a bay-like indentation off the floor of a huge impact basin. That basin's 740 kilometers in diameter, and the valley itself is only about 50 kilometers long, 35 miles long, something like that. It's I'll shift units here. You'll have to excuse me if I use all sorts of different units. You realize that we built our rockets and spacecraft using the English system of measure. We flew them, in deference to the Navy, using the nautical system of measure. We've always talked about nautical miles and flying it, but we worked on the moon in the metric system of measure. And after some 35 years, sometimes you may find me get them mixed up, and I apologize for that. But the valley itself is only about 7 kilometers, or about 4.5 miles wide, and we landed right at the, somewhere I saw well, that's all right. We landed in the middle of the valley, just at the narrowest point, just ahead of that plume-like geological deposit that you see there in the valley itself. The mountains on either side are over 6,000 feet high. So this is a valley, even though it doesn't look that way in this particular view, it's deeper than the Grand Canyon of the Colorado. And we landed within a few meters, really, of where we planned to land before we left the Earth. So it's a tribute to the people who figured out how to navigate in deep space, believe me. And they really figured it out. And all the missions, with the exception of Apollo 11, which is a special case, landed just as precisely. Pinpoint landings, literally, on the moon. Another view, that last picture was from about 100 miles away, nautical miles away. This one's from about 15 nautical miles away. And in the middle of the illuminated portion of the picture, you'll see the other spacecraft, the America. Ron Evans now is all alone, piloting the America. He's about a mile ahead of us and below us somewhat, phasing his orbit so he would be out of the way when we began our powered descent into the landing site. Now I only had one good view of the valley before we landed, because my job, which hopefully will be taken over by automated systems when we return to the moon, my job was to make sure Gene Cernan had verbal information from the computer that would tell him where the landing site was relative to the instrument he had in his window. And so I was continually giving readouts to him verbally from the computer. And so to do that, I couldn't look out the window very well. So that was that. However, right after pitchover at 8,000 feet, I did have a chance to look out. And believe me, we were not at 8,000 feet. We were essentially looking across the top of these mountains, and very quickly we were down in the canyon itself. The lunar surface looks very much like what you see here, relatively undisturbed, except by the effluence from the descent engine. The metallic object in the foreground is one of 16 small restartable rockets, we call attitude control thrusters, that were used to control the orientation of the vehicle during flight. Those had only about 50 pounds thrust. Now remember what I said about the thrust of the individual engines of the first stage of Saturn V. They're 1.5 million pounds. So there's a tremendous spectrum of technology between those two engines, rocket engines. Amazing what was done for that time. There's a Challenger now in its home environment of the moon. It weighed about 14 metric tons. It performed flawlessly for us and for essentially all the other missions, with some very minor exceptions, small issues that never kept us from landing on the moon. I took this picture as one of three early on in the first excursion from the Challenger in order to document what things looked like before we really stirred it up, as you'll see later. And you see my tracks going out. They actually left a path. There's dark material underneath what appears to be a light covering around the spacecraft. That's actually caused by a change in the optical characteristics of the surface due to winnowing. As the engine effluents came out, they took the fine material away and left a more highly reflective coarse material that made it look like it was a light covering. But it gradually disappears, as you can see out there, as you move away from it. And anytime you felt a little bit homesick, you could look up and see the Earth, only 240,000 miles away at this particular time. Gene Cernan took the first test drive of the lunar rover, creation of the Bendix Corporation, General Motors Corporation, and the Marshall Space Flight Center as the manager of that. It only weighed about 450 Earth pounds. Remember, divide everything by 6 to know how much it weighed on the moon. We had independent power, electric power on each wheel, front and rear wheel steering. Really a very, very effective field vehicle. It would go at full speed over this kind of terrain, 6 to 8 miles an hour. That doesn't seem like much, but remember, 1/6 gravity. Anytime you're going to hit a bump, you're going to be off the surface. And we had it up to about 12 miles an hour once coming downhill. And I think even the great Navy test pilot, Captain Cernan, thought that was a little bit fast. It does seem like you're really moving at that speed when you're bouncing over the surface like we were. Now, well-dressed, excuse me, a well-dressed geologist astronaut wears what you see here. This is, again, on the first excursion. I'm not nearly as dirty here as I was going to get. The upper part of my suit, at least, is not yet gray. I've seen, this suit, by the way, is in the Smithsonian. It's in sort of a morgue-like facility in the Smithsonian. It really is sort of an interesting experience to see a suit that you wore on the moon pulled out on a gurney with your name on it. I hope that doesn't foretell the future too quickly here. I'm taking what we call a rake sample. We're trying to get a certain size fraction of the lunar debris, or regolith as it's called there, that contains, we found from other missions, contains more material thrown in from other areas than just a normal sample would. Yours truly, the suit and the backpack there, weighed about 370 Earth pounds. But on the moon, about 61 pounds. So working on the moon was really quite easy. Running, walking, it was really, the suit was, it was stiff, but I could use a cross-country skiing technique and move very quickly over the surface and very comfortably. The only part of this whole work that was physically demanding was the use of the glove and the forearm muscles. The glove was a balloon. It was the shape of your hand, but it was a balloon. So every time you squeezed it, you had to use these forearm muscles. Just think about squeezing a tennis ball continuously for 8 or 9 hours. And that's essentially what we were doing. And so getting these muscles in shape is extremely important. We knew it was important, but frankly, we did nothing like the training that the current shuttle space station EVA astronauts are doing. They are in far better condition today than we were. I thought we were in good condition, but we're not even close to what they're having to do when they do EVAs working with the space station. Again, I was inside this suit. We were staying cool because of that water-cooled underwear, and it was cooled in turn by the sublimation of ice. I don't know how many swamp coolers are used in Pensacola anymore. It's a little humid. We use them all the time in Albuquerque. It's a great cooling system. But that's basically what we had. We had a swamp cooler, except it was ice rather than water. When you expose water to a vacuum, and we had a porous plug there to do that, it would freeze and then sublimate, and that would provide cooling. much of the same way that evaporation of water provides cooling here on Earth. This large boulder was the largest, but we knew it was there. We'd seen it on pre-mission photographs taken by the Apollo 15 astronauts as they went over this site. It's had rolled down the mountain from about 1.5 kilometers away, and yours truly is there for scale. And if you look very carefully in the just to the right of the peak, at the top of the boulder, you'll see a little spot. That's the lunar module again. It's about 3.5 miles away. And again, that white area is just is sort of around it because of the winnowing of the fine material. You see it, pretty much. You don't? Well, let me go back. Let me see. We gotta get you to see that. I'll put my. It's right above my finger there. See that spot? Oh, to the right of the peak of the rock. That's the lunar module. Seems like a long way away. Now this boulder, when it rolled down the mountain, left a track in the soft debris regolith of the moon. And if you look carefully, you'll see my footprints coming down into that track, out of sight, and then up the other side. Now those footprints will stay there in recognizable form for 1 million, maybe 2 million years. So if you want to leave your footprints in the sands of time for a little while, the moon's not a bad place to do it. Certainly much better than Washington, believe me. There you see, that picture was taken after 2 of our 3 excursions. And you see that debris around the lunar module now has been significantly disturbed by our activities. It's very firm to start with, very high bearing strength. Many of you have tamped sand, and you know you can get sand. If you tamp it long enough, it gets pretty firm and very high bearing strength. But if you start to walk around on it, well, it loosens up. Well, the same thing happens on the moon. And that stabilizing that material is going to be an issue for long-term inhabitants of the moon, but I think there are many ways to do that. You can use aggregate or maybe even microwave it, because most of it's glass. Over 50% of that material is glass, and it probably will center very nicely. It is also the source of one of the only resource that we've identified that might be worth bringing back to Earth, and that's the subject of the book that was mentioned earlier, Return to the Moon. It's a light isotope of helium called helium-3. It is a nearly ideal fuel for fusion power production. And my colleagues at the University of Wisconsin back in 1985 and 86 identified this as a potential resource. About 13 years after we knew it was there, nobody had recognized that it was potentially a power resource for the Earth, and we've been working on that since, trying to figure out how to implement a program to bring it back and use it as a clean energy source here on Earth. It also, the regolith contains hydrogen and helium and nitrogen, all of which, along with the helium, have come from the sun as part of the solar wind. And because the moon has no atmosphere, as we illustrated by that earlier picture, that solar wind at very high velocity is embedded in the individual fragments of the debris that's there on the moon. And it's preserved for us to harvest at some time in the future for future generations. This doesn't prove I was on the moon, but people seem to like the picture. It is one of, between our excursions, I think this was actually after our 3rd excursion, and I'm looking a lot happier than I really was about leaving. I would have preferred to stay for at least another day or 2. There are a lot of things I didn't get done, and I would have liked to have gotten done. But we certainly did get dirty while we were there, no question about that. Departure from the moon was actually filmed for the first time by the television camera that was mounted on the lunar rover that some of you may have seen in better definition than this. But it was really quite a spectacular sight on television. Inside the cabin of the lunar module, we only had about a ½ G acceleration. You could feel it. You sort of did that because you were standing there in 1/6 G. But then it was very ordinary. It seemed very ordinary from all the simulations and everything that we had done. The one thing that happened to me, though, I was basically, in addition to being the backup pilot, with a backup set of controls and things like that. I was the systems engineer. I took care of communications and propulsion and environmental control systems and things like that. And right at the instant that we lifted off, all we had on the communication link was static. That's all we could hear. They could hear us, it turned out. We couldn't hear a thing. And of course, Cernan, as the commander, was getting very upset that he couldn't hear the ground talking to him or anything like that. And I said, I didn't do anything. Well, what it turned out, it took about 2 minutes to finally get that figured out. But they figured it out on the ground. With all the preparation that we did, all the simulations we did, what we call mission sims, somehow we missed the fact that they were going to do a communications handover at exactly the second we were lifting off from the moon. It was just two different groups working, and just coincidentally, it turned out that it was exactly the same second. And that handover didn't work very well. So they dropped off one antenna and didn't bring up the other one, and that was what all the static was about. There's what's left of the lunar module, looking more like a pumpkin, I guess, or than a spacecraft. You realize that we didn't have to worry about aerodynamics. The Flash Gordon spacecraft were not necessary for the moon. There's no air to worry about, and so you could make it any shape you wanted so long as you knew where the center of gravity was and it wasn't too heavy to land. The command module at this point, we're just working our way around Ron Evans in the command module and getting ready to dock at the rendezvous, and you just saw that picture there a moment ago. There's the Command and Service Module America. That open bay is filled with remote sensing equipment, cameras, and radar and other equipments that were used for a couple of days working on the moon. And there's Ron Evans. Let me go back once. I just want to point out the cone-shaped part there that you see is all that we brought back to Earth. That's the command module. The rest of it's the service module. That command module is now resting semi-permanently, I guess, at Space Center Houston. And those of you who are down in Houston sometime soon, you can go up and put your hand on it and see the home we had away from home for most of the mission, as a matter of fact, except for the 3 days on the moon. The Ron, gets his day. He unfortunately passed away quite a number of years ago, far too young to have done that. But in the mission itself, Ron seemed to be having a lot of fun. One of the things he did was to do our traditional demonstration for the hydrogen community. Where's our hydrogen guy here in town? There you are. They hadn't quite worked out how to keep hydrogen out of the water that was produced by the fuel cells. And we like to rub that in. And Ron did it here by getting that hydrogen bubble of reconstituted food to coalesce in a nice little circle or partial sphere in a bag of salmon salad. Now, we always use salmon salad for our experimentation. Salmon doesn't travel well. It somehow always ended up in our food menu, even though we supposedly had control over that food menu. And I think it's because it always came back, and so they just recycled it and hoped they could find some gullible crew to eat it. If you go to museums and see a lot of salmon salad out as food that the astronauts ate, don't believe it. I don't know. I guess John Young liked the salmon salad, but most of us brought it back. Or used it for an experiment like you see here. Just before we left the moon, we had a crescent Earth, from full Earth to crescent. I took this picture at what was called AOS, Acquisition of Signal, as we were coming around, getting ready to leave, and we were soon headed back towards home. Reluctantly to some degree, but it's always good to go home. That's a view of the moon that I took as we were leaving. It's a nearly full moon. But the right third of it is the far side of the moon, the part that you normally don't get to see unless you've been doing some things that you probably shouldn't have. And it is the part of the moon that is particularly exciting now as we talk about returning to the moon and with the capability eventually of landing back there and of possibly deploying a large-scale radio telescope on the far side of the moon. The reason that's of great interest is that the far side of the moon is always protected from radio interference from the Earth. And it is, for 13 days out of every month, it's protected from radio interference from the sun. And so you have the ability to get a pure, low-frequency signal from space. And it is particularly a signal that we've never been able to see before that that will tell us something about the very, very earliest origins of the universe. It's something we can't get any other way, at least not in the vicinity of this planet. So the return to the moon has many, many aspects to it, primarily as part of a long-term plan to get to Mars. But it also, there's a lot we don't yet know about the moon and what its relationship to other planets like the Earth is. We've learned a great deal, but there's always a great deal more to learn. And then using the moon as a platform in space for really advanced astronomy and other activities, comparable activities, including looking back at the Earth. Being able to monitor the Earth as a full sphere on a continuous basis is something that we can't get from the current satellites that we deploy for weather and Earth science purposes around the Earth. The return through the atmosphere was not, it was uneventful in terms of the plan, but it was quite exciting. As a matter of fact, probably the most dynamic part of the whole mission. The Saturn V, as some of you recall, reached about 4 Gs at 2 minutes and 45 seconds during launch. We peaked at 7 Gs during our early entry activities into the atmosphere, and then held 4 Gs. That 7 Gs was to make sure we were captured. It turns out the spacecraft really does fly. I mean, it doesn't look like a wing, but if you put something in the atmosphere at 35,000 miles an hour with a little bit of an offset CG, it's going to act a little bit like a wing. And it actually has lift, generates a lot of lift. So we had to be sure that we had the lift, what we call the lift vector, down to make sure we dug into the atmosphere, captured, and then we would fly. Then it would fly itself using that lift vector at about 4 Gs and going to where it thought the carrier was. Well, it knew where the carrier was supposed to be. In fact, the Navy early on became concerned enough about the accuracy of our landing back on Earth that they moved the carrier about 5 nautical miles away from that spot to make sure we didn't have a carrier landing, which we would have survived, but it would have been an uncomfortable part of your day. But after, at about 20,000 feet, we put the drogue chutes out to slow us down even more, and then at 10,000 feet, the main chutes that you see here were deployed. It always seemed like they were taking forever to deploy, but they always did. And then we had splashdown for the last of the Apollo series in the Pacific, not too far from Samoa, and the whole sequence was over. All that remained was the old aircraft carrier Tycho. Anybody here serve on the Tycho? Yeah, I'm surprised. Usually in a Navy community, you find people who served on the Ticonderoga. It was eventually decommissioned and I guess sold for scrap. But Captain Green was waiting for us there right on target, and the helicopters picked us up and took us back to that carrier, and the Apollo 17 mission was completed. This picture is a good way to summarize and to end it all with just a little history. That as much as 35 years later we can talk about history. Whoops, it keeps sneaking in there. The flag of the United States symbolizes not only what those 450,000 young Americans did during Apollo, But it symbolizes what free men and women can do when they are given a challenge that they believe is clearly worth meeting. And that's what John Kennedy did for us. Eisenhower started it, really. He laid the groundwork for the technology of the Saturn V. Very important initiatives on his part a year, 2 years before Kennedy made his announcement, and really enabled that announcement to be credible. But it was Kennedy we were responding to at the time, and a very important point is made by the symbolism of the flag on the moon. Behind the astronaut there and the moon itself is the South Massif. It symbolizes what in the history of science, the first time humankind has been able to begin the understanding of a second planet and relate it to its own home planet. That will continue through the future ages, but this was the first time that happened. The astronaut, yours truly, and if you look carefully, you'll see Gene Cernan, who took this picture, kneeling to the left of the flag, reflected in my visor. That symbolizes the technology base that was created at that time, probably the largest explosion of technology in a short period of time that's ever occurred in human history. And then, of course, the Earth above the flag really does symbolize a new status that we have in our solar system, that we can actually look back and see our home planet with no guarantee of return. And that really broke the psychological bonds of humankind, I think, the human species to the Earth, and ultimately will make us a creature of the solar system, at least, if not of the galaxy. So with that, and that shameless plug that you've already seen about Return to the Moon, if you want to see another view about how we might do it, just pick up that book. Thank you very much, ladies and gentlemen. I'm happy to take questions. I'm going to go ahead, right there.
Doctor, tell us
Since I can't see you,
Doctor,
maybe we can bring the lights up.
Okay. Doctor, please tell us your vision for helium-3 fusion power. What are your heart of hearts dreams for the future with helium-3 fusion power?
Well, my dream right now is that you're that angel investor that will provide the initial capital to get us off the ground. And actually, that initial capital doesn't get us back to the moon. What it does, it takes advantage of the first spinoff of helium-3 fusion, and that is to produce positron-emitting isotopes. Now, you may wonder, what are positron-emitting isotopes? Well, they're the isotopes that make it possible for positron emission tomography, or PET diagnostics. And positron-emitting PET diagnostics now are the diagnostics of choice in determining the stage of cancer. It's used hundreds of thousands of procedures now in the United States every year. Extraordinarily important technology, but it is not available to people outside of major urban centers, because these positron-emitting isotopes decay so fast that you can't transport them very far. You have to be in a major urban center for the capital investment in a cyclotron to be enough to afford to have PET diagnostics. So we think there's a major business opportunity there that would get the process started, headed towards actual ultimate fusion power. The technology path is very clear, and there are many of these spin-offs along the technology path. But the final vision is that from the time that angel investor shows up, that in about, and maybe it has happened, I don't know, in about 15 years from that time, that initial investment, that we would have our first shipment of 100 kilograms of helium-3 back from the moon, enough to power the first operating fusion power plant, which is part of the plan, the development of which is part of the plan, power that plant for 1 year, and then begin to continue to resupply and expand the number of power plants. That plant, that would be a 1,000 megawatt plant, standard size for a big power plant, and would begin the process of spreading this technology, very clean technology, not only throughout the country but throughout the world. That's what our dream is. And I say our, I'm including the group, my colleagues at the University of Wisconsin, led by Dean Gerald Krasinski in the engineering department there. Let's try one over here, and then we'll go back over there.
I just had a question regarding what you see as the right balance between manned space flight versus like JPL kind of machines, and also the balance you see between the private sector like the X Prize versus government-funded NASA sort of projects.
The balance between robotics and human exploration, I think, is reasonably clear. Certainly, when you're going into new environments that are currently inaccessible to humans, either because of the risk or the distance or the cost, then robotics can fill the gap before you can get human beings there. And we've just had conversations today about what is the proper mix between robots and humans doing cooperative work, and we don't know that yet. But almost certainly there's a role. We just don't know how that meshes. Normally, take myself as an exploration field geologist. I've never used a robot in the field, and nobody I know has. So we're going to have to learn whether robot field assistants, as they're called, actually enhance the productivity of the team, or whether they detract from the use of the unique attributes of humankind. Now, what are those unique attributes of the human explorer? The first one, of course, is the brain. It's a supercomputer that has, I think, at least 4 billion years of evolution behind it. That is something that we don't yet know how to duplicate. It's qualitative or semi-quantitative as a computer, but it's a magnificent machine, if I may use that term. Coupled with that are two things. One, a unique optical system, stereo optical system, the eyes, that are magnificent tools, and the hands, which are extraordinary manipulators. Now, we tend to reduce the effectiveness of the hands because we haven't figured out how to really use the human hand in space. And that's one of my big upsets with NASA, I can say publicly, is that we're just not putting the resources into dealing with the glove of the spacesuit like we should. And there are reasons why that's not happening, funding reasons and other things. But with those three things working for you, the human being is a unique operator in space because we can be reprogrammed instantaneously. You don't have to even think about it, and you're off on a new set of parameters that you're going to use in an exploration environment. Lewis and Clark demonstrated it. We've demonstrated it in space. It's demonstrated every day. It's demonstrated in the laboratory. I mean, people at this institute are building robots, but they're not using robots to build robots yet. You use human beings to do that. And we have to remember that those attributes are there, all the three that I mentioned. And there's a fourth one that is very important, that's human emotion. Human beings are passionate about what they do. And that adds another dimension to what space or any other exploration activity of any other kind means to humankind. And without that emotion and the motivation that comes with it, the stamina that comes with it, you just are not nearly, or robots would not nearly be as productive. Now, some of my colleagues would argue, well, I can provide that emotion and passion and stamina remotely. I can do teleoperation. But the lack of on-the-spot accessibility of the other three attributes that I mentioned really makes a big difference in the productivity of what can be done in space or in any other exploration environment. Many of my geologist friends, and I agree with them, have said that all of that time we spent with that magnificent rover called Opportunity on Mars, trying to figure out what's going on in the Treasury, day after day after day, going there. That was 30 minutes of work for a human being. And plus you would have had a lot more information than we have today. So it's a mix. There is a balance. We don't quite understand all of that balance yet. I think right now it's very good. I think we're getting a great deal of information from Mars. We've got a mission going to the outer planets now, the New Horizons mission, There are many of those kind of things that human beings aren't going to do yet. Someday, maybe, but not yet. And so robots gives us that advanced reconnaissance that I think are very important. But we also know that human beings do some very unique things as well, and that we need to find whether there's what the right mix is, if there's a mix at all, in the use of robots and humans simultaneously.
Dr. Schmidt.
Yes.
I'm back here in the corner.
Wherever you are, yes.
Okay. They gave me a microphone. As an
Was that a mistake?
Perhaps. I'll let you judge that. As an exploration field geologist myself, I kept hoping against hope that you would encounter an outcrop of a marine limestone, perhaps akin to the Lake Valley limestone of southwest New Mexico, during your exploration. Can you explain for the audience a little bit about the rocks you did encounter, their geological history, and if you'd like, feel free to use technical terms.
Well, we're still arguing about the origin of the moon. But one thing we know, it's never had a standing water or even any water that is detectable now. I'm sure it had some water at the time of its origin, but that has all disappeared for various reasons. And so without the water, the Lake Valley limestone wouldn't exist on the moon, or any sedimentary rocks in the classic sense. Now, we use sedimentary rock terminology and logic on the moon because things are thrown up into the lunar vacuum and they come back down. And so there is superposition, which is one of the most fundamental concepts in geology. It was first articulated to our knowledge by a Dane who went by the Latin name Steno, and he in the 1500s. And he is considered sort of the first person to recognize a fundamental principle in geology, and that is the law of superposition, and that is that old things are below young things. Now, it doesn't always work out that way when you get into the details, but nevertheless, most of the time, that's a good proposition in geology. And in the 1500s, particularly in the, shall we say, the restrictive religious environment of the time, it was very daring for a person who actually was a Catholic monk to come up with those kinds of ideas. So we're very proud of him. And then, of course, there have been many of those kind of heroes over time. The first geologic map of any known geologic map of the Earth was done by an Englishman, William Smith, and that map is just a classic. It was beautifully done and really still holds up today. And that was done in the 1700s, if I remember correctly, 1700s. At any rate, the moon is a very unique place. It is basically like it was 4 billion years ago. Now, the big arguments that we have today in our science is what happened between 4.6 billion years ago when the solar system was forming and 4 billion years ago when the moon as we see it today was pretty much intact. There have been some changes, but not very many. Most of my lunar science colleagues, planetary science colleagues, would say that the moon formed as a result of a giant impact of a Mars-sized asteroid on the Earth, and then the debris from that impact, because it was just at the right angle, ended up going into orbit around the moon, around the Earth, and coalesced into the moon. I think there's some real problems with that hypothesis. They like to call it a theory. I'm going to call it a hypothesis, and we won't get into the technical details tonight, but nevertheless, I argue that at the very least it should be treated as a hypothesis rather than an assumed way. It happens sometimes in science, far too often probably, and even maybe in engineering, where an idea takes hold, it becomes very popular, and we forget about that it is just a hypothesis, and that you should be testing that hypothesis. And that's one of the reasons that I am so excited about getting people back on the moon from a science point of view, is to test that. There are some very specific things that we can do in a return to the moon to test that so-called giant impact hypothesis.
We have time for just a couple more questions.
Stand by. Microphone.
Sorry, and as a geologist, You mentioned briefly the impact theory and this low-angle impact of the speculated planet Theia low-angle impact. What is the petrology of the moon rock compared to Earth? I have seen moon rocks in Houston in the museum there, and that space rock looked sort of basaltic.
There are
It's a comparison between moon rock and basalt on Earth or not?
Yes, the dark parts of the moon, what we call the Maria, or form the face of the moon, the man in the moon or the rabbit in the moon, those dark areas are underlain by basalt, by a rock composed primarily of silica, oxygen, alumina, magnesium, iron, but they are unique. We don't see the details of the composition of those rocks is very different than the Earth, but the overall silicate structures are the same. One of the big differences is there's absolutely no water in these rocks. Basalts on Earth have up to 5% water and usually have 3 or more percent. There's just these rocks on the moon are very, very dry. Plus, their isotope compositions are very different and things like that. The light areas of the moon, which constitute most of what you see when you look at a full moon, are pulverized material. The crust, they're primarily composed of aluminum, of silica, oxygen, aluminum. They're what we call anorthosites. They're, for those of you in the audience that want some arcane terms, geologists are like lawyers. We use terms so nobody else will understand what we're talking about. But nevertheless, they're very different. That's the crust of the moon, as we call it, primarily made up of that material. I think there's a general consensus, and this is one I do agree with, is that the outer 500 kilometers at least of the moon was molten at one time and crystallized in layers as a function of the density of the minerals that were crystallizing at any given time. And the lightest materials, the less dense materials, were these what we call feldspars, calcium aluminum feldspars, and that forms this anorthositic crust. But the petrology of the moon is really the problem that the people who advocate a giant impact hypothesis have, because there is a suite of materials. We call them pyroclastic glasses. They're volcanic glasses that have come from very deep within the moon. We know that. There are ways to determine that. And the non-glass component of these pyroclastic glasses, the effluents that drove them up through the lunar crust and caused these eruptions on the moon nearly 4 billion years ago, 3.5 to 4 billion years ago, they are totally incompatible with a giant impact hypothesis. The giant impact hypothesis, they're very rich in volatiles. And the giant impact hypothesis requires that the material ejected from the Earth get very, very hot, 3,000 to 6,000 degrees C. And those volatiles aren't going to be there. So as of now, that hypothesis has no way to explain the composition of this non-glass component of the moon. And there's some other problems with it, but that's really the number one.
We have time for just a couple more questions.
Dr. Schmidt, thank you for your time and your service both. My question tonight is, do you believe that the development of carbon nanotubes and ultimately space elevator concept is important for commercializing the moon, or should we look more towards surface launch vehicles and technology in that realm?
Well, I think carbon nanotubes, driven by, if in part, by some interest in a so-called space elevator, are going to have a long-term important role to play in technology used by human beings. I am not expert enough to say whether we're ever going to be able to use them as a material for a space elevator, or even if a space elevator is feasible, since it takes a very special set of conditions where you can locate a space elevator to get it into orbit. There are many places on Earth. In fact, I think there's only one that people think is reasonably stable that you could deploy a space elevator to. But still, like everything else in science research and engineering research, you never know where it's going to lead in terms of other applications or even that application. And so, you can probably do research in things that are so far off the wall that you'll never get anybody to even think about them. But stepping out at the edge of what we know how to do and maybe a little beyond that edge, I think is extremely important. Ken Ford and I were talking about that today. And getting funding to do those adventurous kinds of research projects is the tough part of it. But to not do them means that you're going to delay the impact that such technologies could have on human society for the best. And so I'm always looking for ways in which you can get funded things that nobody else is going to fund. As long as there's one foot in good science. You've got to have that one foot in good science. You don't want to get out there so far that it doesn't make any sense based on what you know today about science.
Thank you.
Ladies and gentlemen.
One more question.
One more?
Yep.
Thank you again for being with us this evening. As NASA prepares in the next 10 to 20 years to return to the moon, what roles have they designated for you and your Apollo colleagues to assist in that effort?
Next question. No, I'm not being fair. I'm not being fair. Many of my colleagues, including myself, are acting in advisory capacity to NASA, particularly with respect to the Constellation program. Some of them are working with the groups in Houston. I chair the NASA Advisory Council. Owen Garriott, who is a Skylab astronaut, but part of my generation of astronauts, is on that council, as Neil Armstrong just recently left the chair of the Aeronautics Committee of that council. NASA has reached out pretty vigorously to gain the experience that remains in that group of people. We are having a conference, not NASA, but NASA knows about it. And I'm all for these kind of conferences. It's totally independent of NASA, but it's going to be at ASU next week, looking at a very specific part of the lunar landing sequence, namely from about 300 feet down. And we've got Dave Scott there, Dick Gordon's going to be there, I'll be there. And we're going to try to give them at least some of our experience of that phase of flight as people outside of NASA begin to think, both industry and academia, begin to think about how do we do it the next time? What does that experience give us? And then I think midsummer there's a conference at MIT that looks even broader, looks more at the guidance and navigation component, the software component of how do you implement the GNC for the new Altair landing vehicle? So that and there will be calling in people who have landed on the moon and flown these spacecraft to do that. So I think to the degree that the Apollo astronauts want to work and help, I think the opportunities are there, and NASA is making those opportunities. Mike Griffin, the administrator of NASA, is very much attuned to getting as much of the graybeard advice and counsel as he can, because it is an experience base that is very broad. Unfortunately, it is shrinking and disappearing, and now's the time to gather it in. Thank you very much, ladies and gentlemen. Enjoyed it. Thank you. It's not an option, which I strongly recommend to you. It notes that during the Apollo 13 crisis, he did a rough calculation of the average age of the young men and women who were then in the Flight Control Division, basically rescuing Jim Lovell and his crew. And that average age was 26. And we have to remember that when we talk about going back into space, we talk about doing any large-scale activities, you have to have that really a core of young men and women that provide the imagination, the motivation, the stamina that is necessary to carry off these kinds of projects successfully. It is a major issue for the country right now in how we stimulate our own citizens to take on those kinds of, the kind of education that allows them to participate in these kinds of projects in the future. NASA is approaching a time where they will have something like 25% of their workforce retire. And that's not only true of NASA, it's true of a large component of the aerospace industry. And that, who's going to fill in behind that 25% is a major issue that the NASA Advisory Council is dealing with. Ken Ford is sitting on that council with us now. And it is something that all of us have to worry about. Okay. Well, thank you very much, Ken, and thank you everyone here at the Institute and the fine tour I've had today. It's just really been enjoyable. And I do believe this is my first return to Pensacola since I was given a check ride by a gentleman here in an audience and turned loose after only 8 hours in one of those H-13s. When they told me we were going to solo after 8 hours, I said, "You're crazy." But they turned us loose, and that's great. Ladies and gentlemen, what I want to do tonight is take you on a very quick trip to the moon, talk a little bit about both history and some of the things that might happen in the future in the context of that trip. Of course, we began it, as this gentleman down here has reminded me, with a launch of a Saturn V, the largest rocket used by human beings to go into space so far, and indeed will probably stay that way. The Saturn V weighed, okay, we'll move quickly now. We've talked about Saturn V. We also did a great deal of geological training. This is yours truly there on the left, my robot assistant on the right, Gene Cernan. Actually, Gene, like all of the commanders of the missions from Apollo 13 on, became excellent field assistants, in fact, to some degree geologists, through a training program that we put together. Part of this training was, for the last 3 missions at least, we had about a week a month actually out in the field, working actual projects unknown to us, but following through in a simulation-based set of procedures, doing as much as we could exactly what we would do on the moon. Of course, we didn't wear our pressure suits, space suits, but we used all the equipment we had available. You can see the backpacks and everything that were simulated, but nevertheless enabled us to not only learn the geological aspects of exploration, but also to get the procedures down so they were pretty much automatic, rote, and we wouldn't waste a lot of time on them. Now, the reason I show this picture is not to show how I've aged, but to give some of you, and particularly these young people in the audience, always are wondering what all of those colored valves and entry ports are on this spacesuit. This is the Apollo exploration space, 6.8 million pounds, fully fueled. Developed 7.5 million pounds of thrust with the initial first stage, the 5 big engines that were in that stage. And as I said, really was a remarkable accomplishment. Those of you who may have glanced at my book, I still say that over the long haul, it's probably the concept of a rocket system that would sustain us best in long-term access to space. But be that as it may, there are other circumstances that have required NASA to move towards a shuttle-derived system, primarily economics, relatively short-term economics, because tooling is available for that new rocket, where it's not available to the Saturn V any longer. Now, the trip to the moon required, as many of you are aware, some 450,000 Americans to work together. Only 50,000 of those people were actual government employees. The rest were part of the contractor team that supported that mission. Okay. And most of those people were young. Gene Kranz, in his book, Failure Suit, the blue ones represent inputs into the suit, and the red ones represent outputs. Our oxygen, our communications, our water. We had, you know how we stayed cool on the moon? Besides our personalities, of course. We had water-cooled underwear. And in fact, today I just saw one of those water-cooled underwear that they're using up here in some of their experiments here at the Institute. It really is a wonderful way to stay cool. In fact, more seriously, it is what we would call an enabling technology. We could not have spent 8 hours straight in this suit working without some kind of technology like that, other than air cooling or gas cooling. We had to have that water-cooled underwear. Now, the way I'll talk a little bit more about how we cool that probably in a few minutes, but this spacesuit was really an extremely important part of the Apollo program. It's another spacecraft, really. It had everything you needed to work outside the lunar module for about 8 hours. Actually, we were pressurized in it probably for more like 9.5 to 10 hours. And it could be recharged every night or every rest period. Of course, the moon, night and day is a little different than down here, but every rest period we would plug in the water and recharge the water, plug in the oxygen.